Okay, hey, AP students. This is solution stoichiometry, the second lesson, lesson 2. Today, what I'm going to go over with you guys is kind of some basic calculations that we've done already. I mean, my goodness, you were already tested over a lot of this stuff, but just to kind of remind you about numerically how we measure solutions, in particular molarity, how we do dilutions for changing from one concentration of a solution to another concentration of solution. And then at the end, we'll talk about solution formation in terms of heats of solution and how polar solvents and polar solutes will mix, while non-polar solutes and polar solvents actually would not mix. So there's a little bit of thermochemistry that goes along with it. That's not really what we're going to test you guys over, but I do want to demonstrate and show you kind of how it fits in at least a little bit to this. And it is covered in these chapters, as I'm sure you know from your reading. But anyway, let's get started here. I've got to pause this for a second and I'll get it started. Okay, so now we can get it started. Let's see, share this content. So we'll go through and do a few problems and discuss what those ways that, to actually numerically measure some of the calculations that are associated with these stoichiometric calculations, but anyway, or solution calculations. So so we're going to review those associated with solution composition and talk about some of the procedures to make dilutions. We're also going to talk about the heats of solution in terms of how solutions are formed, and it's a one way to determine whether indirect or thermic, but we'll get there. So composition of solutions, in order to perform these calculations, you actually have to know the nature of the solution, whether or not they're going to actually mix, polarity, most importantly, and then you have to know the amounts of those things that are present. The way that we do that is by measuring sort of how much of something is dissolved in the entire solution. That is called molarity. And so what molarity is literally the moles of solute divided by the liters of the entire solution. Now, the solution is going to be composed of two things. It's going to be composed of the solute and the solvent. But the denominator of molarity is always all of it together, the volume of the entire solution. So let's do a quick molarity calculation just to remind you how to do them. I might do a couple of these actually, but anyway, it says calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. It would be helpful to know actually what sodium sulfate is. And I noticed that your polyatomic ions are still something that you are struggling with, so that's not good. But this is sodium sulfate. Sodium with a +1 charge needs 2 of them to balance the 2- charge of sulfate. In order to solve for the molarity is actually calculated as the moles of the solute divided by the liters of solution. So I will need to change this number of grams of sodium sulfate into moles. To do that, I'll need to calculate the molar mass. Now, I would just tell you the molar mass, but having witnessed and seen your exams, it might be a good idea for me to review that process real quickly. Here is sodium, sulfur, and oxygen, which are in sodium sulfate. There are 2 sodiums, a sulfur, and 4 oxygens. Each oxygen has a mass of 16.00, sulfur is 32.07, and each sodium is 22.99. You would multiply each of those by their respective numbers in the actual compound. You would get 45.98 grams here, 32.07, of course, here, and 64. When you add these together, you're going to get 142.05 grams per mole, or just grams is okay, but that's how many grams, that's its molar mass. That's how many grams would be in 1 mole of sodium sulfate. To find the molarity, I need the number of moles of that divided by the total liters of solution. Now it says it's put in enough water to make 125 milliliters of solution. So what I would do if I were doing this problem is I would write 23.4 grams of sodium sulfate, and we're not changing to another compound, so I can just write sodium sulfate kind of once in my calculation there. That's fine. But I got 23.4 grams of sodium sulfate, and I would go ahead and put the volume in the denominator. Essentially what you're doing is you're just setting it up like it's a like it's a density problem, really. But 125 milliliters of solution in the denominator. What I need to do is change that milliliters. I'll do that first to liters, 1,000. Oh, not 1,000 liters, Tom. 1,000 milliliters is 1 liter. I've done that conversion to liters for the denominator, and then I would need to change from grams to moles. So 145.05 grams of sodium sulfate is 1 mole of sodium sulfate, and I would get my answer. So my milliliters are canceling, my grams are canceling, and I'm left with moles per liter, which would be correct. The answer in this particular one is 1.32 molar. Now, if you guys go and look at my key online, which it's the same PowerPoint I'm showing you now, it'll be calculated a little bit differently, which I'll show you. But this is how I would do it. It's that many grams of sodium sulfate and that many milliliters of solution, and then you just do it as a dimensional analysis problem. It's a little bit easier, I think, to do it just as a single problem, but what you could have done is separated them. You could have taken 23.4 grams divided by the molar mass, found the number of moles, and then in a separate calculation divided by 0.125 liters. That's fine. You can do them separate, but don't round in between steps. That's kind of why I like sticking it in a single dimensional analysis problem. But anyway, so here, let's do another one. How many grams of sodium sulfate are required to make 350 milliliters of a 0.5 molar sodium sulfate solution? This right here is a conversion factor. It is 0.50 moles of sodium sulfate in 1 liter of solution. So they're giving you this right here as a conversion factor. So what you're going to do, what I would do, is you have 350 milliliters of solution, right? I would change that to liters of solution and then use your molarity as a conversion factor to find moles and then molar mass to find the grams. So here I have 350 milliliters. I would change my milliliters of solution to liters of solution. And then my conversion factor from liters to moles is going to be my molarity. And at that point, I can use my moles to grams using my molar mass. And it's the same compound. So 142.05 was my molar mass of my sodium sulfate. And I'll get my answer, which is actually 25 grams. That's how I would solve that. Oh, sorry, guys. I'm getting a phone call, which I don't need. Okay, there we go. 25 grams. This is how I would solve the problem. You could simplify this a little bit by changing your milliliters to liters without doing the conversion, just saying 0.350 real quickly. And notice I have 2 sig figs because 350 is only 2 sig figs. So is the molarity. But anyway, a simple, straightforward problem, just going from grams using molarity as a conversion factor. Much like the last workout problem on your exam, actually. So here you go. That's pretty much the same way, except here on the PowerPoint, we've left off the change from milliliters to liters, but essentially it's the same. So here's a dilution problem. And I had a few kids emailing me in the middle of the lab saying, well, we don't know how to do the dilutions. You already did the dilutions. Well, what do we need to do dilutions with? Well, okay. So the molarity of the stock copper solution that we created, or that I created in the video, using the penny and some copper, I don't remember what the concentration was, but whatever it was the stock solution, and you make dilutions with it to produce the other ones. Pretty easy to do these. The way that you do them is you use the formula M1V1 equals M2V2. Because volume is on both sides of the equation, it doesn't really matter whether you change from liters, or excuse me, to milliliters to liters, or leave them both in liters, or leave them both in milliliters. Unless they're specifying, it really doesn't make any difference. So I like to list my variables on these, and it doesn't matter as long as you group them together. It says what volume of, so what I would be looking for is the volume of, and I'm going to say that this will be my M1, or my first compound here. And this would be 1.00 molar potassium nitrate. Listen to me, one compound, one solution. We want to get a 1 molar solution from, or we want to use a 1 molar solution as our stock solution. And then we want to put, change it to, 500 milliliters of a 0.250 molar solution. So my M2 here would be the 0.250 molar potassium nitrate solution. And my volume 2 here would be 500.0 milliliters. Now the calculation here is actually quite simple. 1.00. I'll leave my units off to save myself some room. 0.250 and 500.0 mils. My ending answer here really is 125 milliliters. It only asked for what volume of that you would actually need to produce this solution. Excuse me. You will actually have to be able to describe in words how to create this solution. And I'm going to go ahead and do that here, even though it's not really in the PowerPoint. It is a little bit later, but whatever. Is I would say that you take 125 milliliters or obtain 125 milliliters of 1.000 molar potassium nitrate. And you could get crazy here and say in a graduated cylinder. Sure. Or you could say using a graduated cylinder, measure 125 milliliters of 1 molar potassium nitrate. So you're going to place 125, this 125 milliliters in a 500 milliliter volumetric flask. And add water to the etched line. Oh, and add, that's right. Water is distilled water is DH2O. Add DH2O to the etched line. That is sufficient. That would get you through your AP test. Had this been a strong acid, you would say you want to add a little bit of water before you add the acid and then top off with a little bit more water. We'll get to that and discuss that a little later. But it had this question, and it didn't, but had this question asked for, how would you prepare a solution of? You'd have to do the calculation to find your milliliters, and then you would have to give a description of how you actually are going to do that. So, but yeah, like I said, it was really only asking for the volume, but good for us to review that as well. So a standard solution or stock solution is one where the concentration is known, is accurately known, and then you can use volumetric flasks, or you could use pipettes. We're going to use volumetric flasks for the most part, especially if it's solids dissolving. And we've already used, have we? No, I guess we didn't, because you guys did this virtually because COVID, sorry. We would have used volumetric flasks. You guys would have created a liter of solution and then gone and done your own dilutions, which would have been very helpful. But we will get the opportunity to do that again in another Pierce Law lab soon. But anyway, what you would do is put the substance, whether that be a milliliters. You've got to stop. People have got to leave me alone. Okay, hang on. Let me just turn this off. We could have put 125 milliliters in here and added up to the etch line with distilled water. You want to swirl while you do it, but it's okay to just say add water to the etched line. But like I said, we'll be doing this again later in the year. We'll do some with solids and we'll do some with solutions. Yeah, and volumetric flask is absolutely the best way to do this, as it is most accurate. So solution composition, solutions can be concentrated or they can be weak, or concentrated, excuse me, or they can be dilute. Dilute means that you don't have a lot of the molecules in solution. It's not the same thing as weak, however. So, I mean, when you think of concentrated Kool-Aid, you think is like strong, it's strong Kool-Aid. But strong and weak refer to their properties, like a strong acid dissociates readily in solution, where a weak acid does not. A concentrated acid that's weak can be very dangerous, even though it's weak. So the two are very different, and it's important that you understand the difference. Concentrated and dilute are what talk about the molarity, the concentration. The strong and weak refer to the behavior of those substances and whether or not they dissociate completely. And so the strong and weak part, you'll have to just memorize. The concentrated and dilute, you numerically determine what those are. And there's a cute little graphic, right? So the strong ones wield swords, and if there's a bunch of them, they would be concentrated and strong. If they were dilute and strong, they would, of course, be fewer of them in the same volume. And of course, they're wielding swords. Whereas if you looked at, concentrated and weak, just a couple of those would be strong, dissociating or wielding their weapon. And then, of course, if there weren't very many of them, that would be dilute, meaning not very many. And of course, there's only one wielding a sword to be weak anyway. Cute little graphic. So another way to describe a solution is looking at the mass of the solute in terms of the mass of the entire solution. it can be done in what is called mass percent. And you're familiar with this. We did some of this in pre-AP, where you have grams over grams, or you can say it's a 50% by mass solution. They do a lot of this in biology. They'll say, oh, I need a 10%. They ask my lab aides and I to make some solutions for them. And they'll say, we need a 10% glucose solution, which means 10 grams of glucose in 90 grams of water, or 10 grams of glucose in 100 grams of solution. They're very easy to make. They're not as precise as our molarity calculations are, but it's kind of the same thing. It's fine. Another way to do it is outside of the percent solute is to, or mass percent, is to do what's called a mole fraction, which is basically a mole percent. You do the solute moles divided by the total moles. And so these are the formulas. Both of these, actually, I'm not sure both. I know the bottom one is on your formula chart. But this is mole fraction on the bottom. I do realize that it's got sort of a script X. That's not a script X. Kind of a script X or whatever for your mole fraction. It's usually lowercase too, if that matters, but it'll show up on your formula chart. The N is the number of moles of one of the substances. Notice the same one shows up on the bottom, and then the other one is the number of moles of either the solvent or solute or some other substance that's present. And so you just have the moles of all of it on the bottom, the moles of each thing that's in the solution. And it can be more than 2. It could be 3 or 4 or whatever. And then the number of moles of what you want the fraction of just on top. Very simple. It's the part over the whole. Very easy to do these. And we'll do a couple calculations of these as well. So this is kind of a long problem. I believe, yeah, this is it. A long problem. And I'll go through and do each part. But what they've given us is a bunch of data, and they're asking us to find the molarity and the mole fraction of this solution that's prepared from ethanol and water. Excuse me. So, yeah, like I said, this is kind of a long problem. But knowing kind of what I know about this, there's a few things that they kind of left off in here that you need to know, but they probably should have put it in the problem. It says a solution made using 10.5 grams of ethanol in 1,200 milliliters of water to make a final volume of 10.5 mils. Find the molarity and the mole fraction. Okay, so one of the things that we're going to need to know is the number of mole. To do mole fraction, we'll need to know the number of moles of ethanol, and we'll need to know the number of moles of water. So to do molarity, we'll need to know the number of moles of solute, which is the ethanol, and we'll need to know the total liters of solution, which they actually have already given us. They did give it in milliliters, but it's the same thing. Let's go ahead and go find the moles of both of them, and then I'll go do the calculations on a separate slide. But if I've got 10.5 grams of ethanol, which is C2H5OH, I can change that to moles very easily. 1 mole of ethanol is 46.08. Now I've done the calculation ahead of time, but it's just 2 carbons, 6 hydrogens, and an oxygen. 46.08 grams of C2H5OH, C2H5OH. And then what you end up getting is approximately 0.288 moles of our ethanol. Anyway, so that's one of the moles. The other one we had to solve for moles is the water in order to do mole fraction. So I'll just go ahead and do that now. They say it's 1200.0 milliliters of H2O. So you would need the density for this one, I guess, since they didn't tell us grams, but that's okay. Density of water is 1, so it's 1 milliliter is 1 gram of water exactly. So the total mass here of the water would then be 1200.0 grams. If I want to change that to moles, I would divide 18.02 grams in the denominator here and 1 mole of H2O. I'm leaving my H2O off all these, my bad. And I can solve for the number of moles of water, which ends up being 66.59 moles of H2O. So right there, I've got, excuse me, both of my, and that's 62.59. Sorry, my handwriting's kind of sloppy. 66, yeah, 66.59. So those are my 2 moles. And so if I have both those, I could go solve for mole fraction. It asks to solve for the molarity and the mole fraction of this. So I'm going to go ahead and go do that here on this next slide. But for molarity, the molarity would be the moles of my solute divided by my liters of my solution. In this case, the moles of the solute are the ethanol, 0.288 moles of the ethanol divided by the liters of solution. The milliliters total of solution they gave us up here at the top, they said the total volume was 1210.5 milliliters. I could do the conversion, or I could just say it is actually 1.2105 liters, moving it over 3 places. And I can solve for the molarity. The molarity for this guy would be 0.188 molar. And had I gone and solved for, let's see my script X, my mole fraction, it would be the number of moles. I'm going to write ETH down here for the ethanol. And in the denominator, the moles of the ethanol plus the number of moles of the H2O. So the moles of the ethanol were 0.228. Oh, I wrote 288 up there. I apologize. That's 228. 228. Did I mess up there too? Okay. 228 divided by the 0.228 plus my moles of my water, which were 66.59. And I get my mole fraction. Mole fraction here would be 0.00341. And there are no units for mole fraction. It's just a percentage. So you've got moles divided by moles. They cancel out. It's over. So this is definitely something you'll have to do. We will ask you to calculate mole fraction. In fact, in your homework, there's several of these asking you to calculate mole fraction molarity. And they're used basically to tell you what the concentration of the solutions are. So here's kind of the PowerPoint version of the same thing. Same answers we got above, kind of condensed. And they're also taking the liberty of assuming that the solution has a density of 1 gram per mil, even though the ethanol's there. It's a pretty good, especially to just a couple, maybe even 3 sig figs, it's still accurate. So this brings us to the last part, energies of solution. This is kind of a difficult thing for students to wrap their heads around, because I'm going to like show you pictures of solutions forming and arrows going in different ways, and students get confused. We will revisit this again when we come back to thermochem in December, or actually in like November, December, and then we'll hit it again at the beginning of the spring. But anyway, this will be kind of our first foray into it here. But what happens here is you're going to, there's several different steps in what happens in a solution formation. Now you just put 2 things together and go, ooh, it made a solution. But in reality, if you have water and we added the ethanol, like in the last example. So what had to happen is the water sitting there and you put the ethanol there. Well, for the ethanol molecules to actually get in between the water molecules have to actually separate. And we call that the expanding of the solute and the expanding of the solvent. Doesn't matter which one happens first, but they both have to separate apart from their individual molecules to be able to get between the molecules of the other one, the solvent or the solute. And so there is a certain amount of energy associated with this. So compounds that have a great deal of polarity, like water, have higher delta H values or heats of solution. They have heats that are the amount of heat necessary to break these molecules apart. And if they're attracted to one another greatly, it takes more energy, and so it requires more energy. And so their delta H values would, of course, be larger values. Also, the amount of energy to break up the solute and break up the solvent is energy that must be put into it. So that energy value would be positive, which is kind of an interesting thing. You never think about that. You're like, oh, you give off heat. That means exothermic. It means it's a negative delta H value. It doesn't work that way. If you have to put energy into something, it's actually a positive delta H value. Anyway, so what happens here is you have to put in energy to break up the solute, put in energy to break up the solvent. And then as they go back together, there's a certain amount of energy that happens that may be positive, but usually it's kind of a negative amount of energy. They actually become more stable as they get closer to each other and start to form interactions and attractions between them. And so here's the graphic that I'm talking about that kind of freaks students out a little bit. And you don't need to be freaked out. So this over here says enthalpy. This is basically the energy, okay, the amount of energy or temperature or whatever that's being input in order for this to occur, to break up those solvent molecules and to break up those solute molecules, particles. It's going to take a certain amount of energy that is put into the system. That is called this delta H1 or delta H2. It doesn't matter which one's which, but there's one for the solvent. And then there would be one also for the solute. Now they don't overlap each other. What we're doing is we're adding up the total amount of energy necessary to separate all those particles apart. Now, on a molecular level, it doesn't really work this way. It kind of happens over a little bit of time. You pour it in there, they separate and they mix and whatever. But in order to do the calculations, you have to totally do it separately. So all of it separates, all of it separates. How much energy is that? And then all of it comes together. How much is that? Now, in reality, this would occur over time. But to do the calculations, we just have to say, boom, it happens. So here we've got them all separated up at the top. And then right here, it says that this energy value goes down. So this is delta H3, which is actually the heat of solution formation. And then what happens after that is there's a certain amount of energy that is between these two, like from here to here. That is the delta H of the reaction. Now, in this particular case, it would be solution formation, but it would be the amount of energy. Since more energy is given off when the solution forms, energy would be given off like this. So this delta H value would actually be negative. And so in this case, it would feel hot when the solution was produced, which is interesting. Not all solutions are like that. And so we're looking at the same thing, except in this case, the amount of energy given off when the particles collide and move together is less than the amount of energy that has to be put in. If that's the case, then that means that this delta H value is actually positive. And these two things don't form solutions well. Or if they do form solutions, energy has to be put in order for that solution to form. So if you saw in the previous one, there was more energy given off by the solution formation than it took to break them apart. In that case, there's excess energy. The solution forms without any outside intervention, and it's basically spontaneous. We will get to that way later. But it'll happen without any outside intervention. In this case, it needs energy in order to occur. And so it's going to pull energy from the surroundings or you will have to give it energy for it to happen or whatever. So in this particular case, if you put your hand on the glass and this was happening, the glass would feel cold. It would take energy from you in order for this to dissolve, which is interesting. But anyway, just kind of showing you that. Now, if you have two solute and solvent molecules that don't actually mix, then it gets kind of weird. And then you end up with really large positive values, meaning it takes too much energy for the solutions to form, and they don't actually form solutions. And I'll show you that in the last slide here. It's a little confusing, but don't worry too much about it. So the heat of solution is equal to the sum of the heat produced or consumed in those three steps. And you add all three of them together. The first two going up were positive, and then the heat of solution, if it's really large, it actually would have enough so and those values, are negative. And so when you add them all together, you end up getting a negative value, which would mean the solution is exothermic and would happen. If you end up getting a positive value, it's still possible that it'll happen if it's a very small positive value. So looking here, it says, if the heat of solution is very positive, meaning that it requires a lot of energy for it to occur, then energy has to come into the system to make that solute dissolve, which is what I was talking about. And what happens is the substance is basically insoluble unless you put energy into the system. And it may require a ton of energy. Now, if it's pretty close, if it's just a little positive, usually you can get it to dissolve. Or if the value is negative, it dissolves really easily. And in this second bullet here, if the heat of solution is very negative or only slightly positive, like I'm saying, the energy is leaving the system, and so there's enough energy for it to occur, and so it does dissolve. And we say that solute is in fact soluble. And that reaction probably would be exothermic as a result. Now, there's a table here that summarizes all these interactions, and it's confusing, and it's got a lot of nonsense in here. But just focus on these last two parts here, the outcome. No solution forms when you have really large positive values. In other words, much more energy would have to come into the system in order for them to dissolve. And then also no solution forms, look once again, when you also have a large delta H of solution. So once you add all of them together, if you end up with a large positive value, it means that a lot of energy is necessary and you're not going to get a solution to form, regardless of what its polarity is. Now, if you scroll all the way over to the left-hand side here, this is nonpolar polar. Does nonpolar dissolve in polar? For the most part, they do not. 99.9 times, no, they do not. Sometimes they can. And so this is kind of showing you, oh, you can have it happen. And this is, but for the most part, it's not going to happen. And then look down on the bottom, polar solute to nonpolar solvent. Once again, polar and nonpolar are not going to mix. Polar and polar will mix, and nonpolar will mix. Those will be the two solutions that actually form. And heats of solution, which you may be totally confused now, but the heats of solution are evidence that this is the way that it works and that it does, in fact, happen based on polarity. And so while I didn't go through the whole chart here with you, I'm not concerned really about that. We're not going to spend a lot of time on this chart. It's just supposed to help you, and I'm not sure it does. But things that have really strong attractions for each other are going to have large positive values to separate those molecules before you can put them in solution. Things that don't attract to each other very well, like nonpolar substances, will have really small values, and therefore it's not going to effectively form solutions well unless it's with other things with really small values. Anyway, we'll call it quits there. So we will we'll come back in lesson 3 and do a little bit more with solution formation and polarity, and we'll talk about what happens with vapor pressure as a result. But I hope you got something out of this more than just the simple calculations at the beginning. And I'll see you guys. I'll see you guys in the next lesson.